Alright, hi and welcome to Lab 1, everyone. So, this is actually exciting. It's only 50 lines of code or less to complete this lab, but that does not correlate with the difficulty. So definitely start early. I am assigning this lab now, and it will be due week 5. So you have lots of weeks to do it, but there's a lot to wrap your head around, so please get started early. Here's the write-up, and I'll have that ready too. So let us begin. This is something very similar to what we learned about, but let me teach you a new word. It's called satisfiability. Okay? So pretend you have a Boolean expression, something that could be true or false depending on the values of the variables. A lot of the time, you would like to know, it's an important question to ask, if there is some assignment of these variables to truth values that makes it true. Okay, so maybe give a value for P, give a value for Q, give a value for R. Is there some way to make the whole result true? If so, that Boolean expression is called satisfiable. Okay? That's what we would like to show and figure out if possible. So there is what's called a satisfying solution to this formula, right? You could set P to be true. You could set Q to be true. You can set them all to be true, right? And that will make the whole thing true. Right? That'll make the whole thing true, and this is one mapping of variables to truth values that would do it. So that's called a satisfying solution. I'll write it down here, and that's why we call it satisfiability. Okay, and this is more important than you might imagine. So satisfiability checking is everywhere these days. It is used for figuring out if programs are correct, automatically proving that they are correct, analyzing a program to see if it's going to do the right thing and you should trust it. Even compilers do satisfiability checking, because if you have an if statement and the compiler can determine that it will never be true, like its condition will never be true, it does not need to compile it, and it can save time. Isn't that cool? So satisfiability is everywhere in computer science, and so I'd like to teach you how to do it. We're going to find all the satisfying solutions to a given Boolean expression, some formula. Okay? So that's the topic of our lab. It's called satisfiability checking, or satisfiability solving, and SAT solving for short. Okay? Let us review some things from CSCI 41 next, because those are going to come up. All right. One thing that you may or may not have learned in CSCI 41, depends on the teacher, is smart pointers, and you don't have to worry about these. These are just wrappers around heap objects, pointers on the heap, and it manages the memory for you. So it calls new for you and it calls delete for you, and you don't have to do anything extra. So these are a lifesaver. If you've never seen them before, they won't take long to explain. Okay? You can use them just like pointers, and they're just wonderful. So you got to include the memory header for this, and I'll be using unique pointers in my example and shared pointers in my example. Shared pointers are the more common of the two. Okay? But yeah, let's talk about these guys. So smart pointers, they're just classes that call new and delete for you automatically. You can use a star, you can use the arrow, just like they are normal pointers, but the type looks different. So instead of saying T star all over the place, you can say either unique pointer of T or shared pointer of T. These are both equivalent to T star in a special way. All right? If you want to make something, make a T on the heap as a unique pointer, you use the library function makeUnique of type T. And then you give all the T constructor arguments after some parentheses. Okay? So that's how you make a unique pointer. You do the same thing with a shared pointer. You say make shared of T, and you give all the T constructor arguments. Okay? So the main difference between a unique pointer and a shared pointer is that a unique pointer can only be owned, we say, by one person. So let me show you some code about this. Boop. So I've made a C class, just a silly little class called C with a destructor that prints out when it's being called, because I'm about to show you that this code is automatically deleting things for us. So let me show you the very start of it. Boop. So here is how I can make a unique pointer to an int on the heap. P points there, and I can say make unique. So make an integer as a unique pointer on the heap, give it the value 42. Okay? And so just think, instead of saying unique pointer int, read that, but see int star in your mind, okay? Because it works just like an int star. I can set the value, I can get it out with the star. Not a big deal. So this will print 42, and also it won't leak any memory. It calls new and delete for us. Oops. So G++. So I got my 42. Isn't that neat? So it's automatically calling new right here, and it's calling delete once we are done with this P, okay? Once it goes out of scope, so once main finishes, it knows that we're done with it. It's super nice. All right, I can do the same thing for the C's. I can make a C, a unique C, on the heap, call it P2 as the pointer to that thing, and then I can use it. Let's see, where do I want to go with this? Let's move the comment. And just by saying this, I now have a C on the heap. The one thing you can't do with a unique pointer that you could with a normal pointer is move it around, copy it. So I can't make a copy of that pointer and set it equal to P2. A unique pointer can only be owned by one person. Okay, so there's a way to get around this. It's called move. I'm not going to deal with it right now because we're not going to use it in our lab. All right, that's the one thing you can't do. That won't even compile, actually. So that's a unique pointer, and it calls new and delete for us. So we don't have to worry about it. Once it notices, once C++ notices that we're done with P2, so at the end of main, it will automatically call the destructor and free the memory. So you see the destructor being called, even though I never said delete anywhere. Isn't that awesome? So that's unique pointers, and then shared pointers are just things on the heap managed for you that can be owned by multiple people. Okay? So here's like P3, a pointer to an int on the heap, make shared 43, and it's essentially us saying, that line above is us saying int star P3 equals new int 43 with some extra cool stuff that makes it so that we don't ever have to say delete. Okay? So here is cout star P3. It just works normally like a pointer. You can use all of those operators. Okay, so here's the final output here. And so this was outputting 43. I can make a shared pointer to a C in P4. I can set P5 equal to P4. That totally works because I can share these pointers. I can copy them around. And I can set the fields. The arrow operator works just as normally as it would with a normal pointer to a C. Set it to 44, print it out through P5 instead. So we see the 44 there. And now this one C that we made on the heap will get destructed, just like this one that we made on the heap got destructed. So it's automatically calling delete for us, and we're not leaking any memory at all. Okay? So you won't have to worry too much about this. I'm going to give you a bunch of shared pointers in the lab, and you can just use them like normal pointers. Okay? You don't have to ever delete them. They get automatically deleted for us. Super nice. So that's smart pointers. And then something that you should remember from CSCI 41, everybody should be teaching this, right, is inheritance. So let me give you that final example that everybody loves to give with inheritance, the cats and the dogs and the animals and all that. So let's go there. So an animal class can be a base class. So every animal has a name, right? So we'll put that up here in the animal class. Every animal can make noise, so we'll have a talk method. So we'll put that in the base class. Same with like getters and setters. We can have a get name method and a set name method. And they all live up in animal, and we can inherit all of this functionality. So this is a base class, and we don't want to duplicate this code. So we're going to put it in one place in a class called animal, and then we're going to inherit from it in subclasses, cat and dog, for example. So a cat inherits from an animal. A dog inherits from an animal. It should always have a name. It should always be able to talk. And let's keep all of that functionality up in animal because everybody needs that. Every animal needs to know all of that stuff. And the reason we have inheritance is for sharing code, allows for code reuse. And the reason, or the time that you notice you need it, is when you have an is-a relationship, right? A cat is an animal. A dog is an animal. And so that's when you know that inheritance is a good idea. So a cat, in addition to having a name and a talk method, maybe it has like a favorite toy, and that could be down here specific to cats or something. But one thing that you can do is override previously defined methods. So I can override the talk method here. I can override the talk method for dogs as well. So cats say meow and dogs say woof. That's what you can do there. And so we can share the code and override things when we need to. So this is a subclass. Cat is a subclass of animal, and so is dog. Dog is a subclass of animal, the base class. And so they get all this functionality for free. Every cat gets a name because it's an animal. It's inheriting from animal. Every dog gets a name, and the getters and setters for name, because it's an animal. And we know it has a talk method, but we can change that just for us if we need to do something extra special. Okay, so that's inheritance in a nutshell. Hopefully it's all coming back to us. And here is my fun animal example for that. So here's an animal class. It's got a name. This could just as easily have been protected instead of private. And then here's the constructor for an animal. And here is a virtual talk method because we want to be able to overwrite it. Okay, so I'll make it a virtual method. We'll actually make it a pure virtual method so that animal is a abstract class. All right, we cannot instantiate an animal object. We are forced to use a subclass because of that. And then we have a getter. I guess once you set the name for an animal, you can never change it. So I don't give a setter in the animal class. So this is the animal functionality that can be inherited by a cat and by a dog. All right. So here's a cat object, or the cat class. Here's how you can construct a cat object. You got to give its name, and then you can call, using the initializer list, the constructor for its base class, for animal, to go and actually do the setting of the name member variable, which exists. Okay. So we gain that functionality, and then we can override the talk method to do something different, to do something that we want just a cat to do something just that we want a dog to do. Dog is the same, right? So now in main, I can make two pointers, because why not? Let's make two animals on the heap, a cat on the heap and a dog on the heap. So Alonzo is my cat's name, and then Cisco is my friend's dog's name. So that's why I'm using those. So I have C and D, two shared pointers, one to a cat, one to a dog. And one nice thing about inheritance is it lets you view objects from the point of view of their base class. So I can make a vector not of just cats, not of just dogs, but of animals, because they both are animals, both a dog and a cat. So I can put them together like that and use the functionality that is in common among the animals, like the getters for the name and the talk method, which we know exists, but each of these overrode their own. So it'll say meow for the cat and woof for the dog. So that's just a refresher on inheritance. Boop. And so just a very complicated program to print meow and woof, okay, and the names of the animals. So yeah, yell at me if any of that is still confusing, and I will make it less confusing. All right, so that's inheritance, and now we're ready to do Lab 01. There's going to be smart pointers and inheritance inside of it, and remember that our end goal is to perform satisfiability checking. So I'm giving you a formula that you need to determine all of the ways that it might become true. You need to try all the possibilities for the variables and pick out just the cases where you found the ways for it to be true. Okay? So let's go to the write-up. Boop. So get the starter code, here it all is, and we are going to satisfiability solve, or sat solve for short. Okay, so we want to, given a formula, like this one for example, a Boolean formula, we want to find all the ways to make it satisfiable. So maybe true, false, false works, maybe true, true, false works. We want to find every possible mapping of variables to truth values that makes the formula true. That's what we want to do in this lab, okay? So the first thing we need to do is learn how to represent these formulas that look like this when we're writing math. How do we represent that inside of a computer? How do we build up the data structure that represents a Boolean formula, okay? So I've called this the formula class in our lab. And so every Boolean expression, it's a subclass of the formula class. There are special ors and vars and ands and nots, and that's how we're going to build these up. So if you look at all the blue stuff here in this tree, that is how you represent the formula p or Q and not R. Okay? Do you see kind of how you can notice that? So the OR is the outermost operation, and so it is the root of this tree. Every formula is secretly just a tree. Okay, that's the trick. And then on the left-hand side of the OR, I'll use a different color, LHS and RHS, left-hand side and right-hand side. On the left-hand side of the OR is the P. That's how we can represent that. It's a variable called P. And then on the right-hand side of the OR is this whole AND expression. Okay, so the AND is the root of it. And then on the left of the AND, we have the Q. On the right of the AND, we have the not R. And what is not but a not node with the variable that is being negated as its child. Do you see how I can represent every Boolean formula, looks kind of like this, as a special tree? That's the key, okay? And once we are able to represent that, then we can evaluate it to true or false. So let me show you the code for now, and we'll get to evaluation in just a second. So everything that I've defined is in logic.each. So here are all the formulas. So here's the base class for formulas. You can make an AND that takes a left-hand side and a right-hand side. An OR, also you're ORing together two things, right? A left thing and a right thing. When you negate something, you negate just one thing, so I call it inside. It's the thing you're inside of the negation. And then if you have a variable, that is also a formula. It just has a name, the name of the variable. Okay, that's all the data that's associated with this stuff. But it is really just a tree. Here's the left root and the right root. Okay, left child, right child. For and or, there's a single child from that, and then vars are always leaves. They don't have children. Okay, does that make sense? Do you see how I can represent this formula as this tree? That's the first key thing. And I'll be giving you these formulas pre-made. I'll be giving you these trees pre-made. And it's your job, one of your jobs, is to evaluate this formula when someone has given you a mapping for variables and values. Okay, so somebody's going to come along and say, here's my formula f, like this is f. F dot evaluate, given some mapping of variables to values. You got to tell me, because you're going to run into these variables eventually. You got to tell me what their values should be. And that's a mapping that I'm going to call var to val. Okay? So this is just saying, you got to pass this along to evaluate. And so whenever you see P, pretend it's true. Whenever you see Q, pretend it's false. And so on. And here is how you evaluate these Boolean expressions under a given mapping. This is a recursive process. Okay, this is why you see the word recursive call everywhere. You look at the root. This is all going to be done in the evaluate method. These all have evaluate methods. Every formula can be evaluated under a given variable to value mapping, right? A map from variables to bools. That's the idea. So, how do you do it? I have this formula represented as this blue tree, and I have this green var to val mapping. How in the world do I get back true or false based on that? Because this is really true or false and not false, right? How do I do that? It is the magic of recursion, okay? So when you see an OR, it's just a tree traversal, really. You are going to recursively evaluate the left-hand side and the right-hand side of an OR. Because you need to get true or false so that you can OR that thing together. You can OR together the true with the false, for example. So how do you do that? You make the recursive call to the left-hand side of the OR. You evaluate the LHS, for example. And this would be the base case, because you're getting to just a single variable, all right? And so when you have a variable and you want to evaluate it, you just look it up in the mapping. I see a P, oh, just pretend it's true. So the result of this recursive call will be true. This subtree will evaluate to true. So the left side of the OR is the true, and then the right side is more complicated. And we need to AND together Q and not R. So again, there will be a recursive call made. So the AND, now from its perspective, it will make a recursive call to the left to evaluate this subtree. It's going to be a base case because we're at a variable. We can get the value that it's mapped to, which is false. We'll return that. And then the not, we need to do the right-hand side of the AND, which is a not, and it needs to evaluate itself. So it itself needs to make a recursive call. What in the world is the negation of my variable, right? So it needs to get down here, evaluate var r to something, which is false, and then not will, of course, negate that and give back true. And then the whole and now is ready to give back an answer, because it's got the false and the true, and we need to and together the false and the true. So the whole result of this subtree's recursive call is false and true, which is, of course, false, right? So this subtree gives back true, this subtree gives back false, and the final answer now is, because we're ORing those two together, true or false. And so the result of the whole thing is true. And oh man, that means this was a satisfying solution to the formula. Did you see that? So that's my quick explanation. Definitely read my writing down here. It makes a bit more sense. And this is the same example. I tell you exactly what to do, and I also give a lot of comments in the code. So this is a recursive process, because these are trees. You go down the left subtree, you go down the right subtree, you get back true or false from both sides, and then you combine them as necessary, using an OR operation, using an AND operation, using a NOT operation, all that stuff. Okay? So that's the idea there. Recursion is involved, and vars are the base case. You can just look them up in the map. Okay, so that is how to evaluate and represent Boolean expressions in C++. That's how we're going to do it, at least. And so somebody is going to eventually call a formula f.evaluate. Okay? And so I've made a test for that for you in the testing file, testlogic.cpp. Got a lot of stuff going on, but the first one is for your evaluation methods. I'm going to test that. And so here I am making RP or QN not R. So I'm building those up on the heap, of course. So I'm making the variables P, Q, and R. I am negating the R. I'm ANDing together Q and not R, and then I'm building the OR. You see that? That's going to represent this in code. And so I want to evaluate your formula, this formula, in two different mappings. That's what this test is doing. It's doing this one, which should give back true, and it's using this mapping. P is false, Q is false, and R is false. And that one should give back false. That's not a satisfying solution. Okay? So those are two tests, and hopefully it makes a bit more sense now. So that's me testing your evaluation methods, which you will implement in logic.cpp. Okay? So here, the stuff that I've implemented for you, you're going to implement AND's evaluation, OR's evaluation, NOT's evaluation, and VAR's evaluation. Okay? And then after that, you are ready for the second part of the lab, which is actually sat solving. So you're given a formula and you want to find every possible way to assign variables to values. So those are maps of vars to bools that give back true. So every single one of those maps, we're going to have a bunch of them, potentially. A bunch of different solutions. Okay, so it's a set of maps. That's the key. And then you will, this is where the user calls. It'll call the normal sat solve. But the real work is going to happen in the sat solve helper function that takes a formula and a bunch of extra variables that will eventually calculate the correct answer. And this is another recursive algorithm. Okay, so we're getting a lot of experience with recursion in this class, whether we like it or not. That's one of the things you're forced to learn. Okay, so that is an intro to the next half of the lab. Let's get more into it. All right, so the idea is once we know how to evaluate a single formula under a single var to val mapping, we want to create every single possible var to val mapping so we can try all of them with our formula, okay? And see which ones are true, because we want to extract just the true things. We want to see all the different ways that we could make this formula true, right? And so that involves some more recursion. We want to try every possible combination of values for each variable, because we have a P, a Q, and an R in this case. So we want to try true and false for P, true and false for Q, and true and false for R. All combinations. There's 2 to the 3 combinations, right? For 3 variables. We want to try each one of them. They're all true, they're all false, and everything in between. It's like a truth table. So we need to generate that truth table. Okay? So this is done through a recursive function called satSolveHelper, and I would like to show you the intuition behind it. Okay? Usually in CSCI 40 at least, I like to give a algorithm that is recursive that generates all the different combinations of things. This is essentially that all over again, but a bit fancier. Okay? So let me show you how to recursively try all the possibilities of something. All right, so let's pretend we have 3 different variables, x, y, and z, or p, q, and r, it doesn't matter, and they can each take on 3 values. So x could be a, b, or c. Y could be a, b, or c. Same for z. So this is slightly different to what you're going to implement, of course, because every value can only be true or false for this lab. But I want to show you a more generic example, and I will show you in Racket how to generate every possibility. Okay? So let's make a function called print possibilities, and the secret is it's a recursive algorithm that takes 2 parameters, a list of variables that we still need to give values for, I'll call those unchosen variables, and then a list of variables that we have already given values to. We've made choices. Those will be chosen bars, and they will exist with their choices right next to them. Okay? So initially, when we first make the recursive call, the very initial call, everything will be unchosen and nothing will be chosen, right? So in Racket, here is a list with x, y, and z in it, and here is a list that is empty because there is nothing chosen yet. And so that's what we're going to call, and then let me show you in a diagram how the recursion is going to unfold. Okay? So I'm going to shorten print possibilities to just p for my own sake. All right? So we're going to call print possibilities with, these are the variables we need to give values for still, and here are all the choices that we've made so far. This is a very, very wide recursion tree, so I'm only showing you parts of it, but the part that I do show you should make it all clear. Okay? So here's what's going to go on. When you see this, you have variables that you still need to choose values for. I have x, y, and z who still are unchosen. So the trick is, just take the first thing, pick out the x, and give it every possible value. Okay? That's where the recursion comes into play. So I'll then make 3 recursive calls. One where I have set x to a, one where I've set x to b, and one where I've set x to c. And I want to recursively, under these choices that I've made for x, there's 3 different universes, I would like to then choose values for y and z. You see how that's getting smaller? That will eventually cause the recursion to end. That's the trick. So find all the possibilities. That's how you read this call. Find all the possibilities of mappings for y and z after I've already made this one. Okay? And so again, it'll be 3 recursive calls here. I'm not showing you the 3 recursive calls here, 3 recursive calls here. Those also exist. But under this universe, where I've already made the choice that x gets a, let's make the next choice. So I pick off the next thing. I pick off the y and give it a value. You see that? And so then I'm going to make 3 more recursive calls, where I just have z left to choose for, but I've made the choice that y is a, y is b, y is c, in addition to the choices that I've already made. X is a still. You see that? And so that recursion is going to go that way, and it's going to recursively find all the different combinations for z where I've already made this assumption, or I've already made these assumptions. I've already set these values. And so once you get down to these base cases, you've made choices for every possible variable. You are empty. You have nothing left to choose. And here are all the choices that you've made. So at the leaves here of the recursion, you have made choices for everybody, and you can just print them out. Okay? So here's AAA, AAB, AAC, and all these other ... dots that I'm not filling in. Those are going to fill in all the rest. Okay? I hope you see how that's working. That is what you're going to implement. And let me show how it's working in Racket. I've made an implementation of that in Racket for you. And so essentially, you're going to be translating this code to C++. Changing it a little bit because your variables can be true or false, not A, B, and C. Okay? So initially, I'm going to print all the possibilities for the x, y, and z variables, and I haven't chosen anybody yet. Everything is unchosen and nothing is chosen. And then I'm going to run my code. All right? So there's a base case and a recursive case. So I want to print all the possibilities for these variables that I've not yet chosen and these ones that I have. Okay? When you get down to here, you've made choices for everybody, and your unchosen variables are empty. Okay? So that'll get back true. In that case, you can just output your choices. You're done. That's the base case. Okay? You've chosen everything, just output your choices. So that's that implementation there. And then the recursive case is where the work gets done. Okay? That's when you have a choice to make. Like, this is a non-empty list. So pick out the first thing. Make a choice for it. You have 3 different ones. All right? So here's how I take my unchosen vars and I pick out the first thing. There is a nice first function in Racket that takes the first thing of a list. So here is the first thing in that list, and then here's the rest of the list, everything but the first thing. It's called rest. And then I can make my 3 recursive calls, print all the possibilities under for making choices for the rest of my variables under the universe where I have made a choice for this particular variable to be A, for this particular variable to be B, for this particular variable to be C. I'm just making a list of lists in Racket. It's not a big deal, but it'll be slightly different in C++, right? In addition to the choices that I've already made, I'm adding this choice, okay? That's how the recursion unwinds. And so the rest of ours, it's always getting smaller, because it's one smaller. I'm popping off 1 variable, and I'm making my 3 choices. You'll only make 2 recursive calls, because you're going to set the variable to both true and false. Those are your 2 universes, okay? And then eventually, rest of ours has become empty because you've made choices for every possible variable. You'll get down to these leaves of the recursion tree. These are your base cases, where you've made choices for everyone, and now all that's left to do is print out those choices, or use those choices, in our case, okay? So in the base case, we just print out our chosen variables because we've made choices for everybody. There's nothing left to choose. So let me show you this. This is the way we call it. Let me show you it running. And so every possible choice is here. AAA, AAB, all the way down to CCB, CCC. Yeah? So this is what you'll be translating to C++, essentially. Okay? And you can make a fancier version. You can make, this can be your helper function. You don't want the user to care about this. You can just give them the set of variables to begin with and call it with the empty list for unchosen variables. That's something that you can do, and that's essentially what we're doing in the lab. But you don't have to pay too much attention to that here. Okay? That is how you try all the possibilities of things. And so that is the last part of your lab. All right? So your job is to sat solve. You have a formula. You've just implemented all of the ways to evaluate that formula under a given var to val mapping. So you're ready. Now you need to generate every single possible mapping and try your formula for that mapping. See if it gives back true or not. Okay? So this is what the user will use. They'll use the sat solve function on a formula, and you need to give back a bunch of solutions, all right? And the way you're going to get them is to call sat solve helper with the same formula, and here is that recursive algorithm again. So here's your unchosen variables. They're initially always, they start out unchosen, every single one of them. So you're going to put all the variables that exist in the formula here. You can get those from this nice extract var names function, or method of a formula. I've implemented that for you. And then, once you have those are your remaining variables, then you have made no choices yet, so you'll give an empty map to start off the recursion, and then you'll give, as a reference, this solutions set, okay? And you'll just keep on adding to it. You'll give it by reference each time. It'll be the same one, and so every time you find a satisfying solution, you'll put it in this set, okay? That's the idea. And so the recursion is exactly the same. Once remaining vars becomes empty, that's your base case. You've made choices for everybody. You can now call the formula. You can evaluate the formula under those choices. You have made choices for every variable, right? There are no remaining variables. You can evaluate, okay? See if evaluating it gives back true. If so, add that choice, that map, your choices for all the variables, to the satisfying solution set, okay? And if you're not in the base case yet, you have to recurse. So there's at least one value still in remaining vars to be set, either to true or to false. And so you got to extract that var, make a new set of remaining vars, that's one smaller of course, so you can recursively call, and then add that add the choice that you make to your choices map. So you're adding to this existing one. Either that variable that you're picking out is true or it's false. Okay, so you got to make 2 separate maps. One where that variable that you picked out is true, and one where that variable that you picked out is false. Okay, and you recursively try to solve the formula using that choice and that other choice. Okay, and so that'll eventually lead to the base case where you have made choices for every variable. you can evaluate your formula under those choices and see if you found any satisfying solutions. See if you found one more satisfying solution. Okay? If so, you'll add it to this set. And you'll just keep passing along the same thing for this spot in the function. Okay? So please start early on this lab. Ask me questions. These comments are meant to help, of course. Definitely read those. I've spent a lot of time writing them. And that should be it. So the first part is evaluation. Get that working. Get that test passing. And then implement sat solving. Okay? So generate every possible mapping of the variables in a formula to the values, to the true and false values, and then find all the ones that make the formula true. Okay? That is satisfiability solving in a nutshell. So that is, I think, officially all that I have for you. Please start early. This is a lab that's going to be due a long time from now, so definitely take advantage of that. And yeah, ask me all the questions that you'd like. I will be here to answer them. And then you'll only be turning in your logic.cpp file. That's all. Okay? So that is your lab 1 explained. So good luck, and I will see you next week.